Welcome, friends. Welcome to Unit 10, Lesson 3, Properties of Logarithms. Before we begin, I just want to remind you that while you're watching this, you should probably be taking some notes, or as you're listening, maybe have a piece of scrap paper nearby so that you can work out some of the problems with me. In an effort to make this video concise, I'm not going to give a lot of wait time. So remember that you have the power of the pause button, or for that matter, the power of the turn me off button. But feel free to pause, rewind as you need to. My goal here is that if you can have a pretty good understanding of this lesson, you can use the time on Thursday, Friday's block of this week to really work on problems in class, to work with your peers, to ask me, and therefore you leave with a really good understanding of properties of logarithms. And for those of you that are on a field trip and are unable to join us, please make sure that you use the power of the email if you are stuck in any way, shape, or form. I do have a book assignment at the end of this, and I will post another resource for extra practice. So by the end of today, hopefully you will know how to use the properties of logarithms to change bases and model real-life problems. All right, change of base. There's going to be two purposes to the change of base. Some of you might think, well, this is stupid, this is purposeless. I've got a TI-NSpire where it does any base, so I don't need this. It's old, it's archaic, I'll never use it. You might need it in future calculus applications. I did check in with your future teachers, and they said, well, it might not come up often. It does come up. Also, you need to know the change of base in the event, especially on an ACT, if you are dealing with a TI-84 or a scientific calculator and not the TI-NSpire. So in the old days when we had log tables, if you wanted to deal with something like log base 5 of 321, then you had to convert it to the common log, or you had to convert it to the natural log, because those were the only values that were available to mathematicians. So without further ado, here's the change of base. If we wanted to, we could convert something in base 7 to base 16 because it's fun, but here's what the general rule says. And let me give you a concrete example. If I am in log base 7 of 15, let me just give you this example. So what I could do is I could convert it to a different base. So let's do the common log, okay, by taking the new base of the value over the new base of the old base. Okay, so again, for those of you that need more words, what this general rule means is we're going to take the log and we're going to pick a new base, and that can be any base we want. And then I'm going to look at the original value, and I'm going to take a ratio or divide that of the log of the same new base we picked of your old base. Okay. So I picked the common log. I'm going to show you in just a minute that I also could have done the natural log. I could have done the natural log of x over the natural log of a. I could do log base 16 of 7 over, excuse me, that would be incorrect. Log base 16 of 15 over log base 16 of 7. Okay, you can change it to any base. So let's break this down further. And I just did this, but if we want to break down log base 7 of 15 to base 16, I can pick log base 16, and you're going to put the value in the numerator, you're going to put the old base in the denominator. Now, is this really helpful? Not unless we have a TI-NSpire, because on the TI-NSpire, I wouldn't even need to change the base. I could do log base 7 of 15 in my calculator if I wanted to. But notice that if I did want to change the base, if I do log base 16 of 15, and I want to divide that by the log of base 16 of 7, I get the same value. I still get 1.39. What does this mean? This means log base 7 of 15 means what exponent of 7 gives me 15? So that value is 1.39. 7 raised to the 1.39 power, or exponent, is what is going to give us 15. So you might be thinking, okay, great, now that's dandy, but I don't have a TI-NSpire with me all the time. What do I do? Well, you want to stick to the common log or the natural log if you have a scientific calculator or an 83 or an 84. And this isn't very hard. I don't think it's very hard to remember or very difficult to execute. So if I'm still talking about log base 7 to 15, I would not want to convert it to base 16 like I did in the previous slide. because if I did, my scientific or my 8384 can't handle base 16. But it can handle the common log. So I can take log base 7 of 15 and I convert it to the common log of log 15 over log 7. Similarly, you could decide to do the natural log. I could have done log base 7 of 15. All I'm doing is converting it to base E. It doesn't make a difference which base you convert it to. And let me show you. If I use a TI-84, if I hit the log of 15 and I divide it by the log of 7, I still get the exponent 1.39. If I take the natural log of 15 and I divide it by the natural log of 7, I still get the exponent of 1.39. So my point with change of base, since it's a ratio, it doesn't make a difference which base you pick. I could have done log base 1 million of 15 over log base 1 million of 7. I could have done log base not of 15 over log base not of 7, provided not was greater than 0 and not equal to 1. All of those ratios are going to yield 1.39. That's how the change of base works. So now we need to talk about properties of logarithms. And a lot of students will look at these and try to apply normal operations of adding, subtracting, multiplying, and dividing. But if you remember what a logarithm means, a logarithm is an exponent. The why of these problems, why they work because they are all related to a property of exponents. So you're going to see me parallel those in my explanation. So let's think about this. Let me give you a concrete example. If I do 2 squared times 2 to the third, all right, this means the value of 4 times the value of 8, which gives me 32. Remember, these are values. It's kind of important. But if I use my properties of exponents, 2 squared times 2 to the third is 2 to the 2 plus 3. I add my exponents, which is 2 to the fifth, and those are equivalent. So I wanted to give you a concrete example because when you see something like log base A of u times v, these are values being multiplied, just like 4 times 8 were values being multiplied. So what I can do is I can break it down into their individual parts. 4 came from 2 squared, 8 came from 2 to the third. So I'm going to give this value of u its own log base A. I'm going to give v its own log base A, okay? But notice up here, I added my exponents, so I have to add the logs. Remember, this represents an exponent, this represents an exponent, and you're taking a product of the values. So just like you would do that with properties of exponents, it applies to properties of logs. So when you have a product property, then what you end up doing is you add the logarithms when you give them each value their individual log. With that logic, let me do a concrete example for quotient property. If I took 2 to the third and I divided it by, here, let's do a little bit higher. Let me take 2 to the fifth and divide it by 2 to the third. Well, if I just work this out without using laws of exponents, my numerator is 32, my denominator is 8. Those are the values, guys. That is the number I get after I've applied the exponent. So 32 divided by 8 is 4. Okay, keep that in mind. But if I use properties of exponents, I would subtract the exponents, which yields 2 squared, also giving me 4. So 32 and 8 are my values. I can break each of those up. So I have the log base A of u, the log base A of v. I can break them down into their individual parts. But notice with the exponents, I subtract the exponents. Therefore, I have to subtract the logs. Again, a log is an exponent. A log is an exponent. So when I'm using the quotient property, and this applies to logarithms, you end up subtracting the logs. Last property, the power property. So let me give you an example there. Okay, on the power property, if I take 2 squared and raise it to the third power, this gives me 2 to the sixth, which gives me 64. Another way of thinking about it, it's 4 to the third, which also gives me 64. Bottom line, whenever you have a power to a power, you multiply the exponents. So if you're wondering, well, how in the heck does that work here? you have a power to a power. This, my friends, right here represents an exponent or a power. It is being raised to another power of n. So if I've got an exponent raised to an exponent, then you multiply the exponents. So a way of thinking about it is I take the log base a of u, and I'm going to multiply that by n. Most of the time, you will see it written like this, n log a of u. And the reason it's written that way is so that we don't confuse. We're not multiplying the value by n. We're multiplying the entire exponent by the entire exponent. Okay, so how can we apply that? And if any of you want formal proofs, they're on page 444 of your text. Okay, we're going to write each logarithm in terms of the natural log of 4 and 6. So this problem is just trying to get you to break these down and rewrite them. We're not evaluating them. You're not going to come up with a final answer. We're just rewriting them in terms of pieces where the values are 4 and 6. So let's look at A, the natural log of 24. You need to say to yourself, how can I rewrite 24 using my pieces of 4 and 6 that the problem is asking me to rewrite? Well, I'm hoping we're in high school now, so I can rewrite 24 as the product of 4 times 6. Okay. Now, using my properties of exponents, or using my properties of logs, excuse me, I'm going to be using the product property. Okay. The product property applies here. I'm going to give the natural log of 4 its own natural log. I'm going to give 6 its own natural log. But what I have here is a product. And remember, natural log of 4 represents an exponent. Natural log of 6 represents an exponent. Don't ever forget what you're writing and what it means. Well, when I take a product, just like when I take 2 squared times 2 to the third, you add the exponents. So my final answer here is the natural log of 4 plus the natural log of 6. That's how I can write the natural log of 24 in terms of those pieces. Okay, let's look at B. Okay, hopefully you're looking at B and saying to yourself, I've got a quotient. So if we look at the quotient property, you give each of them their own logarithm and you subtract them, because when I look at properties of exponents, okay, if I have x to the third over x squared, I subtract them. So that directly follows. So I have the natural log of 4 minus the natural log of 36. I'm not done. The reason I'm not done is the natural log of 4 is okay. I have that piece. But the natural log of 36 was not an acceptable way to rewrite. So there's 2 different ways you can think about this. This is how I would think about it. I would think about the natural log of 36, and I can rewrite it as 6 squared. And now I can apply my power to a power rule. Okay, so now I'm doing the power property. If you have x raised to the second power, raised to the third power, I can multiply the exponents. Well, what I have in this problem is I have an exponent raised to an exponent of 2. So I can multiply those. Okay, this would be an acceptable final answer. I know some of you might be like, well, what about that 2? You've broken it down into just the natural log of 4 and the natural log of 6. Here's another way that you could have gone with the next step. Okay? Another way that you could have broken this down is the natural log of 4 minus. Now, whenever I put in a minus, the parentheses are going to be really important. I can think of this as the natural log of 6 times 6. So instead of writing it as an exponent 6 squared, I could write it as a product. So when I write it as a product using my properties of logarithms, that means I'm going to add their individual logs. And that parentheses is important, friends, because without the parentheses, we would have had the natural log of 4 minus the natural log of 6 plus the natural log of 6. That is incorrect. You need to distribute the negative. So I have the natural log of 4 minus the natural log of 6 minus the natural log of 6. That is a final answer with full points. This is just a more concise way to rewrite it after we've combined like terms. Our last 2 slides coming up have to do with, I jumped the gun, hold on. We're going to find the exact value of each expression without using a calculator. Let me show you how to do a problem A in 2 different ways. One is to really do it like we did last lesson if we have log base 5, and I can think of this as 5 to the 1/3, a lot of you know that it's just 1/3 because what I'm asking for here is what power of that 5 yields me the value 5 to the 1/3. So that's 1/3. Another way that you can do that is still thinking of this. You still have to do this rewrite step, but you've got a power raised to a power. So I can think of this as 1/3 log base 5 of 5. We've talked about that that's 1. 1/3 times 1 gives me 1/3. It's a little bit longer, but the thought process I think is still worth mentioning. Okay, let's look at B. On B, I see a subtract. Hopefully when you see individual logs being subtracted, you need to think of that quotient property. So I can rewrite this as the natural log of e to the 6th divided by e to the 3rd. Basically what I'm doing is I'm taking the quotient property that we did before. You were given this side, guys. You were given this side. And I'm rewriting it more succinctly, even though I can't say it, log base A of u over v. So when I simplify e to the 6th over e to the 3rd, I get e to the 3rd. And again, two ways you can think of it. This really means log base e of e to the 3rd, so I get 3. Or some of you can use the power to a power rule, so I get 3 natural log of e. This is 1, so 3 times 1 yields 3. Okay, now, for our last two slides, we're going to be, again, some of you might think, oh, this is dumb, this is pointless. And to some extent, it really is math theory. It's your ability to rewrite, because as we use the algebra of calculus, you want to simplify the algebra to make your life in calculus easier. Crummy algebra means awful calculus. Spend your time simplifying your algebra, and then the calculus is not that difficult at all. So we are going to take expressions that are complicated, and we are going to put them into simpler sums, differences, and products. So here we go. We're going to expand. What it means to expand is you are going to have a string of sums and differences of individual logs. In other words, you're going to see the word log or ln multiple times in your final answer. So let's look at problem A. I have log base 4 of 5x to the 3rd y. This is all of your value. And you have to decide, okay, when I look at the value, what is being done there? Do I have quotients? Do I have products? Do I have power to a power? When I expand, I always look for quotients and products first. Then I deal with the power to a power. Okay, you don't have to do it like me, but I'm just to stay organized. The base at this point is frankly irrelevant. It's going to stay the same in whatever we do. So I'm noticing here I've got the product property. I have 3 different bases, a 5, an x, and a y. Each of them are going to get their own log base 4. Then I have to apply the product property. And remind yourself, if I was taking a product of exponents, or of bases, I would add the exponents. Since these are all exponents, friends, remember we never forget what it means when we write it down. I add their exponents. I am 2/3 of the way done. This is an acceptable term. Log base 5 of y is an acceptable term. This is not an acceptable term because I still have a power to a power. So that becomes, whenever I have a power to a power, I multiply the exponents. So my final expanded answer is log base 4 of 5 plus 3 log base 4 of x plus log base 5 of y. Okay. Let's look at B. The first thing I take care of, or I ask myself, is do I have a quotient or a product? And in this case, I have a quotient. So I'm going to give the numerator its own natural log. In this case, we're just dealing with base e. Everybody gets the same base. I'm going to give the denominator. And just as when I take x to the 5th over x squared and I subtract my exponents, remember a log is an exponent, a log is an exponent, so I subtract the exponents. This is why I'm not done. Natural log of 7 is okay, but you have a hidden power to a power here. you can think of the natural log of the square root of 3x minus 5 as 3x minus 5 raised to the half power. So what I have is a power to a power. And whenever I have a power to a power, I multiply. So my final answer is 1 half the natural log of 3x minus 5 subtract the natural log of 7. This is my final answer. Friends, you cannot break this down. If I've got x squared plus x to the third, these are unlike terms. You can't do squat with it. You can't move on because this is a sum. You can't do anything with the exponents. So notice you have values here that are a sum. So at this point, I can't do anything since there's variables. That's my final answer. And for our last slide today, we're going to condense. This means we're going to go in the opposite direction. I'm going to give you something complicated, and I want you to write an answer that only has one log in the final answer. On the previous, when we expanded, I did the quotients and products first, and then I did the powers. So I'm hoping that it's pretty logical that when we condense, I do it in the opposite form. I take care of all of the power to a power first, and then I take care of any quotients or products. All right, so notice, I see this 1 half in front of the log, I see the 3 in front of the log, and they're being multiplied. So this means I've got some powers going on. So I can rewrite this as log of, I rewrote that poorly. I have log of x, we're dealing with the common log since I don't see a base there. Log of x raised to the 1 half plus the log of the quantity x plus 1 raised to the third. So I just took care of my powers to a power. Now I see a plus. When I see a plus, by now, that should ring a bell that if I've got x squared times x to the third, I would add their exponents. What you have going on here, friends, is a product. So I would take the log, and I'm going to take x to the 1 half times x plus 1 to the third. And this is my final answer. You are welcome to rewrite it as the log of the square root of x times x plus 1 to the third. You could write it the log of x plus 1 to the third times the square root of x. All of those are acceptable. It is unnecessary to write out x plus 1 to the third and either use binomial expansion or foiling it out and distribute x to the 1 half. You don't have to do that. I'm wanting you to figure out the products, the quotients, and the powers to the power. I'm not trying to make this more complicated by giving you a bunch of like algebra busy work. Also, I'm not going to give you problems where I'm going to change the bases on you. Ultimately, if like this was a log base 2 and this was a log base 3, you couldn't condense something like that. You would have to use the change of base formula. But again, we're not going to get that complicated. I just wanted to kind of ease your questions about that. All right, let's go to B. Here I see a product. I don't have one here, but let's take care of that product first. I have the natural log of x plus 2 squared minus the natural log of x. So again, I took care of that power first. Then you have to ask yourself, do I have a product or quotient? I'm going to have a quotient because of the subtract. When I have powers, I subtract when I have a quotient. So I'm going to write this as 1 log. Remember, 1 log, and in this case, it's a base e, so we write the natural log, where my numerator is x plus 2 squared and my denominator is x. This is my final answer. I want to be crystal clear. The natural log of x plus 2 squared over the natural log of x is incorrect. I want 1 log. It's the values that are being divided, not the individual logs. This is no credit, nothing partial. It's not correct. It's not equivalent. Okay? If you wanted to write this as the natural log of x squared plus 4x plus 4 over x, fine, you can FOIL that out, but that is unnecessary. All right, last but not least, be careful on these with brackets and tons of parentheses. I have 1/3, and I'm going to distribute that to both terms. So I have 1/3 log base 2 of x plus 1/3 log base 2 of x plus 1. I'm going to do my power to a power, so this 1/3 becomes a power on the x. This 1/3 becomes a power on the x plus 1. Okay, so I just took care of my powers. Because I see the plus, I have a product. So I have log base 2 of x to the 1/3 times x plus 1 to the 1/3. You are welcome. This is an acceptable answer. You also could have written it as log base 2 of the cube roots of 1/3 times that was the incorrect. Get it together now. I could write it as log base 2 of the cube roots of x times x plus 1. Either of those is acceptable. All right, so you might want to write this down in your planner, but I'm not expecting you to do this assignment. I'm expecting you to work on this in class during Thursdays or Fridays block. Certainly, if you aren't going to be present with us, please look at those problems. And I will also put up a worksheet online that is an additional practice. Thank you so much for listening, and see me or email me with any questions. And don't forget, rewind, pause if you need to go back to anything to review.